Imagine looking through a telescope so powerful it can peer across more than 13 billion light-years, far enough that you're not just seeing stars or galaxies, you're seeing time itself, a time when the universe was barely 325 million years old, less than 3% of its current age. No planets, no complex molecules, no life, just clouds of hydrogen gas, the afterglow of the Big Bang, and the flickering birth of the very first galaxies. Now imagine astronomers pointing the James Webb Space Telescope, or JWST, toward a seemingly empty patch of sky in the southern hemisphere known as Good South, part of a larger survey project called JADES, short for JWST Advanced Deep Extragalactic Survey. As its golden mirror unfurls and its ultra-sensitive instruments begin collecting light that's traveled through space for more than 13 billion years, a faint glimmer emerges. Not just any glimmer, a galaxy so distant its light has been stretched, or redshifted, to an almost unbelievable level. The redshift is measured at 13.2, placing it just a cosmic heartbeat away from the dawn of the universe. This tiny dot, now officially catalogued as JD's GSZ 13-0, quickly becomes the center of astronomical attention. But not because of its distance alone, although yes, it is currently the most distant galaxy ever seen. The real shock comes from what lies inside that light. As scientists at NASA and the European Space Agency feed the data from JWST's near-infrared spectrograph, or NIRSPEC, into their analytical software, they spot something that should not exist, not at that time, not in that place. They see oxygen, not hints, not a faint signal. A clear and measurable spectral line indicating the presence of doubly ionized oxygen, known in astrophysics as O3, a specific wavelength of light emitted when oxygen atoms are stripped of 2 electrons by intense ultraviolet radiation from young hot stars. And suddenly the scientific world is faced with a question that doesn't just demand answers, it demands new physics. You see, oxygen is what we call a metal in astronomy. And no, it doesn't mean it's shiny or solid like steel. In astrophysical terms, any element heavier than helium is considered a metal. After the Big Bang, the universe was a near-perfect blend of hydrogen, helium, and a smattering of lithium. Everything else, carbon, nitrogen, iron, oxygen, all of it was forged in the cores of stars. These stars, particularly the massive ones, act like furnaces. They fuse hydrogen into helium, then helium into carbon, and eventually up to iron, depending on their mass. Once they reach the end of their life, these massive stars explode in titanic supernova, spewing those heavier elements into surrounding space, seeding the cosmos with the raw materials for planets, moons, oceans, and eventually life. But here's the thing, that whole process takes time. Massive stars can live fast and die young, maybe in just a few million years, but you still need to form them first. Then you need enough of them to go supernova and enrich the surrounding environment. Then you need a second generation of stars to form out of that enriched gas, in order for that oxygen to show up in a spectrum. So when we see clear oxygen signals in JD's GSZ 13-0, it implies that at least one entire stellar generation has already come and gone. But we're looking at the universe when it was only 325 million years old. That's like walking into a nursery and finding a child writing poetry with the wisdom of an old soul. It shouldn't be possible. Something doesn't add up. This galaxy forces us to ask the unthinkable. Did the first stars form much earlier than we believed? Were they far more massive and thus quicker to explode than our current models predict? Or is there something about the conditions of the early universe that allowed rapid chemical enrichment on a scale we've never considered? To understand how radical this is, consider this. Before JWST, our best view into the early universe came from the Hubble Space Telescope, or HST, which pushed us to redshifts of around 10, roughly 460 million years. After the Big Bang, we thought we were already seeing the baby pictures of galaxies. But JD's GSZ 13-0 takes us over 100 million years further back. And instead of finding a raw, pristine galaxy made only of hydrogen and helium, we find one that's already gone through major star cycles, and it gets even more puzzling. The amount of oxygen detected isn't just a trace. It's enough that if confirmed across more galaxies, it could suggest that the early universe was teeming with activity, that galaxies like this one were not the exception, but the norm. That would completely rewrite our understanding of cosmic dawn, the era when the first stars and galaxies ignited, which brings us to the concept of population 3 stars, hypothetical first-generation stars made entirely of primordial elements. These stars have never been directly observed, but they are theorized to be extremely massive, possibly hundreds of times the mass of our Sun, and to live extremely short lives, just a few million years. Their deaths would trigger the first wave of metal enrichment in the universe. But JID's GSZ 13.0 seems to be saying, that already happened, you're late. So, did we miss something? Or are we just starting to see the real complexity of the early cosmos? This discovery isn't just a curious data point, it's a cosmic revolution in the making. And here's where you come in. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you're captivated by the mysteries of deep space, if you feel that spark of awe every time we discover something that changes how we see the universe, then hit that subscribe button. It's free, it's easy, and it helps us build a community of people who love asking the biggest questions in the cosmos, because we're only at the beginning of this story. The oxygen in JD's GSZ 13.0 is a puzzle piece, but what does the rest of the picture look like? Let's rewind the universe for a moment, not in time but in light. You're an astronomer in a control room, watching as data from the James Webb Space Telescope streams in from deep space. What you're seeing isn't an image, not at first. It's something far more abstract and infinitely more revealing. A spectrum, just a jagged line plotted across wavelengths of infrared light. But to a trained eye, it's a cosmic language, a barcode written in the glow of atoms and the stretch of space-time. And one peak, just one sharp rise in that jagged line, can upend decades of theories. That's exactly what happened with JADE's GSZ 13.0. To the naked eye, or even through a telescope like Hubble, this galaxy would be nothing more than a faint smudge. But with JWST's near-infrared spectrograph, or NIRSPEC, astronomers can split that smudge's light into its individual wavelengths and look for the chemical fingerprints of different elements. Each atom emits and absorbs light at very specific energies, almost like a musical note that only one instrument can play. And among those notes, the unmistakable signal of doubly ionized oxygen, or O3, began to sing. Here's where things get technical and fascinating. The light from JD's GSZ 13.0 was emitted over 13 billion years ago. But due to the expansion of the universe, that light has been redshifted, stretched into longer and redder wavelengths. This is the same reason a fire truck's siren seems lower in pitch as it speeds away from you. The farther away something is in the universe, the more its light is redshifted. By measuring this redshift, scientists can determine just how far back in time the light was emitted. In this case, the redshift measured was 13.2, an astonishing number. For reference, our own Milky Way's light has a redshift of nearly 0. A redshift of 13.2 places this galaxy just 3% of the way through the universe's current age. And that means that every spectral feature we see, every spike in the data, is coming to us from a time when the first stars were still being born. But the signal that caught everyone's attention was not just any feature. It was the unmistakable emission line of O3, which occurs when oxygen atoms lose 2 electrons, typically under the intense ultraviolet radiation of hot, massive stars. This line was bright, meaning there wasn't just a trace of oxygen. It was abundant enough to be easily detected, even from such an incredible distance. That alone was startling. To confirm it, scientists didn't just rely on one observation. The JADE's team used a technique known as spectroscopic confirmation, where light from the galaxy is collected over many hours, sometimes even days, across different filters and instruments. Multiple observations verified that this wasn't a fluke, an artifact, or noise. It was real. The galaxy was not only the most distant ever seen, it was also chemically mature. Now here's where the plot thickens. If the galaxy is 325 million years old and oxygen comes from supernovae, then the very first stars in that galaxy must have formed at least 70 to 100 million years earlier, maybe even sooner. That pushes the formation of stars back to just 200 to 250 million years after the Big Bang. For context, that's when the universe was still full of dense fog, as neutral hydrogen absorbed and scattered all light. This was the cosmic Dark Ages. If stars were already forming and dying in that period, then everything we thought about the timing of star birth is now too conservative. That also raises a critical question. What kind of stars could enrich a galaxy this fast? Astrophysicists have long theorized the existence of population 3 stars, the first stars ever born, made entirely from hydrogen and helium, massive beyond anything we see today. These stars may have lived only a few million years, but they burned incredibly hot, fusing elements in their cores and dying in spectacular explosions that seeded their surroundings with heavier elements, like oxygen. But no one has ever observed a population 3 star. They're theoretical. Until now, perhaps. The oxygen in JD's GSZ 13-0 might be indirect evidence that such stars did indeed exist and formed far earlier than predicted. It also suggests that galaxies in the early universe weren't slowly evolving, but were chemically evolving at breakneck speed. Some scientists even speculate that the density and temperature conditions of early cosmic gas could have led to super-efficient star formation, creating hundreds of massive stars in rapid succession. Let's pause for a moment and appreciate what this means. You're looking at a galaxy that existed when the entire universe was still less than 1/10 the size it is now, when there were no solar systems, no rocky planets, no atmospheres, no trees, no oceans, yet already the fingerprints of life's building blocks, oxygen, carbon, nitrogen, were starting to form. The oxygen in that galaxy may have come from a star that lived and died before our planet was even a whisper in the cosmos. The very same element that makes up 2/3 of the water in your body was already circulating in galaxies over 13 billion years ago. Now imagine what this tells us about the conditions for life in the universe. If galaxies were already chemically mature this early, could planets have formed soon after? Could the basic molecules of life, water, amino acids, carbon chains, have emerged much earlier than we thought? Could ancient star systems, long gone and erased from view, have harbored habitable environments billions of years before Earth? We'll explore those questions soon, but for now, let's not skip over the detective work that made this discovery possible. Measuring a redshift of 13.2 and detecting O3 lines at that distance requires pinpoint calibration, enormous data depth, and the ability to filter out billions of background signals. The JADES team used deep field imaging combined with GRISM spectroscopy, where light is dispersed into spectra as it passes through a prism-like filter. And then comes the painstaking analysis, identifying patterns, checking against models, correcting for instrument sensitivity, ruling out alternative explanations. This isn't just a telescope finding a dot. It's a team of astrophysicists, cosmologists, data scientists, and engineers decoding the earliest whispers of the universe and realizing that those whispers are shouting something unexpected. Let's step back and look at the bigger picture. Because what JD's GSZ 13-0 has revealed doesn't just shake the ground beneath one theory. It ripples outward through nearly every model of the early universe. It's as if we've unearthed a fossil that predates the supposed birth of life itself. And now, scientists are scrambling to redate the timeline. When oxygen showed up in the light of this ancient galaxy, it whispered something audacious. We were wrong about how fast the universe evolved. Traditionally, the early universe has been described as a slow burn. After the Big Bang, the cosmos was hot, dense, and opaque. As it expanded and cooled, atoms began to form, but photons were still being scattered by all the free electrons zipping around. Then, about 380,000 years after the Big Bang, the universe reached a temperature where electrons could finally bond with protons. This event, called recombination, made the universe transparent to light and gave us the cosmic microwave background. But even after that, the universe remained dark for hundreds of millions of years. No stars, no galaxies, just neutral hydrogen, gas and silence. This era, known as the Cosmic Dark Ages, was supposed to end gradually as the first stars ignited and began reionizing that neutral hydrogen. We believe this cosmic dawn began around 400 million years after the Big Bang. But if Jade's GSZ 13-0 contains oxygen, and therefore must have had stars and supernovae long before that, then our cosmic dawn didn't arrive at 400 million years. It may have exploded into being at 200 million years or earlier, and the implications of that are profound. First, it means that galaxy formation may have been far more efficient than previously modeled. In our standard simulations, galaxies emerge slowly, gradually assembling gas into disks and stars through gravitational collapse. But the data from JADES suggests a very different picture, one in which dense regions of the early universe collapsed rapidly, sparking intense bursts of star formation in a very short time. These wouldn't be the gentle spirals we see today. They would be chaotic, turbulent and violent, cosmic pressure cookers where stars live fast and die young. Second, if galaxies like JADES GSZ 13-0 were forming this early and already producing oxygen, it raises another equally startling possibility. Massive black holes, the kind we see at the hearts of galaxies, may have also formed sooner than we thought. Because where there are massive stars, there are remnants. Some go supernova, but the most massive. They collapse inward and give birth to black holes. If enough of these black holes merged or were fed by dense infalling gas in these primordial galaxies, they could form the seeds of supermassive black holes, like the one we see at the center of the Milky Way. In fact, several high redshift galaxies observed by JWST already show surprisingly mature black holes lurking inside them. If those grew from stars that existed even before JADES GSZ 13-0, it begs the question, was the early universe far more crowded with matter, stars and collapsed cores than we ever imagined? That brings us to a third point. The presence of oxygen doesn't just rewrite when galaxies formed, it rewrites what they were like. If galaxies in the first few 100 million years were already chemically enriched, then they weren't simple, pristine clouds of hydrogen. They were dynamic environments, full of feedback mechanisms. Radiation from young stars would have carved out pockets of ionized gas, while supernova explosions could have triggered shock waves that condensed nearby material, sparking even more star formation. This cycle of birth, death, and rebirth, what we call galactic feedback, was already in motion just moments after the Big Bang, cosmically speaking. And here's the twist that really has theorists pacing their offices. If the early universe was full of chemically active galaxies like JADES GSZ 13-0, why haven't we seen them before? Why did telescopes like Hubble miss this entire population? The answer lies in the power of infrared astronomy and the revolutionary design of JWST. Unlike Hubble, which focused largely on visible and ultraviolet light, JWST is tuned to the infrared spectrum, perfect for observing highly redshifted galaxies whose light has been stretched far beyond the visible. These galaxies weren't invisible, they were simply out of range. We've only now built the tools to see them, but now that we can see them, the question becomes, how many are there? Is JADES GSZ 13-0 an outlier, or just the first of many? Already hints are emerging from the JADES survey and others, glimpses of additional galaxies at redshifts of 12, 13 and even higher. Some may even push the frontier to redshift 14 or 15, meaning stars could have existed less than 200 million years after the Big Bang. This changes the way we think about the entire structure of the universe. Dark matter models may need revision. Star formation rates will need recalculating. And the role of galaxies in cosmic reionization, the process that made the universe transparent again, must be reconsidered. It also raises deep philosophical questions. If stars were forming this early, and oxygen, carbon and nitrogen were being produced within a few 100 million years, how early could life have started in the universe? Could other galaxies have formed rocky planets with water-rich environments billions of years before Earth ever cooled? Could life have had a head start? And if so, where is it now? These aren't just theoretical puzzles, they're clues. Each piece of data from JD's GSZ 13.0 whispers something larger, that the universe didn't wait around. It didn't slowly stretch into being. It leapt into complexity, almost as if it couldn't wait to tell its story. And in Section 4, we'll look at what comes next, how astronomers are following this lead, what future discoveries JWST might reveal, and how this finding reshapes our search for ancient life in the cosmos. We'll also dig into the controversies, because not everyone agrees on what JD's GSZ 13.0 means. But before we dive into those final revelations, let's ask the question that lingers over all of this. If the early universe was already filled with oxygen, what else is hiding? Out there just waiting to be seen? Imagine standing at the edge of a vast ancient library. A library that's been locked for over 13 billion years. The door has finally creaked open, and what spills out isn't just dust or parchment. It's light. Galaxies glowing in the infrared, chemical signatures from forgotten stars, echoes of explosions that happened before Earth was even an idea. And now, scientists are rushing in, not to read the last chapter, but to uncover the very first. Because here's the truth. JD's GSZ 13.0 may not be a singular mysterious exception. It could be the first entry in a whole new category of galaxies, primordial, oxygen-rich, and aggressively productive in the earliest epochs of cosmic history. Already, other candidates are emerging from the deep field surveys captured by JWST galaxies at redshifts of 12.6, 13.1, or perhaps even higher. These early galaxies don't fit the expected profile. They're brighter, more massive, and more chemically evolved than our models predicted. Some even show evidence of mature star clusters, rotational structures, or even central mass concentrations. Hints perhaps of early black hole formation or galactic bulge assembly. If these signals hold up under deeper observation, we may be standing on the brink of a new era in cosmology, one where early galaxies didn't simply flicker into existence. They roared into being. But this roaring emergence has sparked debate, and not just curiosity. Some astronomers are skeptical. They point out that while JWST's instruments are powerful, interpreting high redshift galaxies is notoriously difficult. There's a concern that redshift estimates, especially at the far edge of the observable universe, can be contaminated by low redshift interlopers, galaxies or objects whose light mimics that of a more distant source due to dust, strong emission lines, or gravitational lensing. Other scientists question the chemical abundance estimates. Could it be that what we're seeing as oxygen-rich is actually a byproduct of intense starburst activity, rather than a fully matured stellar population? Maybe these galaxies are temporarily boosted by short-lived phenomena, something like stellar winds, collapsing gas clouds, or even exotic interactions we haven't modeled yet. It's also possible that the early universe had regions where structure formed faster than expected, due to subtle fluctuations in the cosmic microwave, background or variations in dark matter distribution. These are not trivial disagreements. They strike at the foundation of cosmology itself. If the timeline of star formation is wrong, if chemical enrichment happened faster than expected, then our understanding of dark matter halos, baryonic physics, and inflation models must be reconsidered. This isn't just about one galaxy. It's about the blueprint of the universe. And yet there's also excitement. Because science thrives in the unknown. Controversy is not failure, it's fuel. Every new observation from JD's, or the Cosmic Evolution Early Release Science Survey, or SEERS, is pushing boundaries. Theorists are updating their models in real time. Simulations once thought too optimistic are now being revived. And perhaps most thrilling of all, the detection of oxygen in JD's GSZ 13.0 has energized a new line of inquiry, the search for biosignature pathways in the earliest galaxies. Let's be clear, we're not saying there was life in JD's GSZ 13.0. It's too far, too ancient, too chaotic. But the mere presence of oxygen, a necessary ingredient for habitability, in such an early environment reshapes the window during which life could have emerged in the universe. If rocky planets formed early, if they had atmospheres rich in water vapor, carbon dioxide, and yes, oxygen, then ancient biospheres could have arisen long before Earth cooled from its molten infancy. This is why JWST's future observations will focus not just on galaxies, but on exoplanet atmospheres. Using its spectrographs, astronomers are already targeting systems like TRAPPIST-1 and LHS 475b, scanning for atmospheric components like methane, ozone, and carbon monoxide, markers that, in certain combinations, could signal the presence of biological processes. What if in the next decade, we detect an oxygen-rich atmosphere around a planet orbiting a star that formed when the universe was only a few 100 million years old? It would suggest that the universe may have always been fertile, and that life rather than a fluke might be a common consequence of cosmic chemistry. In a sense, the detection of oxygen in JD's GSZ 13-0 is a symbol, a red-threaded clue that life's ingredients didn't just show up late in the game. They were there, forged in the hearts of the earliest stars, scattered across galaxies that flickered into existence before the universe had fully cleared its own fog. So where do we go from here? Astronomers are preparing for the next major surveys, JWST's Cycle 3 Deep Fields, the Nancy Grace Roman Space Telescope, and eventually ground-based observatories like the 30-meter telescope and the extremely large telescope, which will pierce the cosmic veil even further. As computational models grow more advanced and artificial intelligence is brought into the fold for spectral analysis, our ability to decode the early universe will accelerate dramatically. But the most profound changes may not be technological. They may be psychological. For generations, we imagined the early universe as silent, sterile, and slow to awaken. But discoveries like JD's GSZ 13-0 challenge that image. They whisper something exhilarating, that complexity was not an afterthought of the cosmos. It was its first language. Now we pass that whisper on to you. What do you think about the discovery of oxygen in the most distant galaxy we've ever seen? Do you believe galaxies were forming far earlier than we imagined? Could life have gotten its start in the cosmic morning instead of the afternoon? Drop your thoughts in the comments. Like this video if your curiosity just expanded like the universe itself. And if you know someone who'd find this fascinating, share it. Because the more we explore together, the closer we get to understanding where we came from and what might still be out there. Until next time, this is Cosmic Whispers, where the past is light and the future is just beginning to glow.